Hi, I'm Sam Baird, and this is our final project demonstration for A Life Challenge 2. My group mates are Jacob Peters, Nathan Arkin, and William Cleveland. I'll start with an introduction and highlighting the key features, and then each of the group mates will go over their specific contributions, and Nathan will finish with a conclusion. So to give an introduction, A Life Challenge is a simulation of artificial life with organisms moving around the world, and each organism has a DNA genome, which is represented by ranges of numbers, its genotype, and the genotype results in discrete phenotypes and traits being expressed. To give a specific example, sleep is a relatively simple trait. So the genotype values between 0 and 25 result in the diurnal phenotype and activity during the day, while values between 25 and 50 result in the nocturnal phenotype and activity at night. And the genome can mutate over time. Different organisms can also form offspring. So in the case of sexual reproduction, organisms that are the same species form offspring by combining their genotypes. In the case of asexual reproduction, organisms can divide and form two offspring. So to give a demonstration of the key features, here is the start screen for the simulation. So to launch a new simulation, you click the start button, and it creates a screen where you can select some simulation parameters. For example, you can adjust the species variability or the number of organisms to start with. Then you click the customize terrain button, and here you can add different terrain features like water, rock, for example, over here. And then you can start the simulation clicking this button. So now the simulation is running. To the left there are various controls, so you can pause and resume the simulation. You can go back to the main menu. You have the option to zoom in and out and pan around the simulation, and then this simulation speed can be adjusted to go faster or slower. To view details about specific organisms, you can hover over them or click to highlight that organism, and then its details will be kept in this panel. Here we can see the organism cycling between sleep and awake. Its energy level, it looks like it actually just died because it has an energy level of 0. Its generation, and then here are some details about the organism's genotypes. For example, it's an omnivore, a sexual reproducer, and has a diurnal sleep pattern. Here at the bottom is a graph, a live graph representing the different species by the color, and the y-axis representing the genotype of that species. To save a simulation, you can click the save button and save it as a file. For example, let's call it test8. And then you can go back to the main menu and load that saved simulation. And we'll start the simulation again from the beginning. And you can see the same terrain features that I created earlier.
Hello, my name is Jacob Peters. I will be focusing on an overview of some of the main contributions that I've made to this project. So, somewhat sequentially, I helped plan out the environment grid that the organisms lived on, the pathfinding of the organisms, the algorithm to determine which species an organism belonged to, and a couple of pages in the GUI. So to start with, Early on, our team decided that the organisms would live on a discrete grid. This would make it a lot easier for us to determine things like collision and movement rather than needing to deal with discrete values or continuous values. So when the simulation starts, the organisms are placed randomly on this grid, and then each frame is follows their behavior from there. At some point, we decided it would be better if there was only one organism per cell, so I went through our code base and refactored that, because initially we had a list of things that could be within a cell, and we wanted to make sure that all the organisms on the environment were visible to the user. Another important thing that I worked on was the species. So you can see each of the organisms are a different color, and that color is unique for a given species. So we had a couple of requirements for this, is that we wanted the species to be based on the organism's genotype. So organisms with similar genotypes should belong to the same species, and organisms with different genotypes belong to different species. Since the simulation may start with a varied number of organisms and variety of genomes, this algorithm should be able to automatically determine the number of species, and that might also change over time. And then we also need it to be stable across frames. So when the simulation updates, the species in the previous frame are more or less the same. So I did some research and I found the mean shift clustering algorithm, and I implemented that using the scikit-learn library. In addition to that, I used the distinct IPy library, which generates random colors that, well, sorry, not random, it generates distinct colors based on a given set of colors so that it's easy to visually distinguish between each organism. I also worked on the pathfinding. So to start each, when it's an organism's turn to be updated in our simulation, they search the nearby grid for other organisms, and they identify what relationship they might have to that organism, and then use that to determine what behavior they will do. So this is prioritized from neutral, prey, same species, and predator relationships. So if there are two organisms within range, but one of them is a predator, then it's going to prioritize moving away from the predator. Whereas if you have some neutral or some same species organisms, then it's going to prioritize attempting to reproduce and so on. So once this decision is made, an organism will attempt to move one cell towards a target. If the cell it's trying to move to is already occupied, then it will handle collision, such as which includes behaviors such as reproduction and predation. And then finally, some of the work that I did on the GUI was creating these two pages. So the first page on the left is the About page, which gives some information about the project. And then on the right is the Customize screen, which shows up when you hit Start for a new simulation. So you get to select a random seed, which is used to set the state of the pseudorandom number generator, the species variability, which selects a number of points within the genome to sample your initial organisms from, and then the number of organisms that are initially spawned into the simulation. And that is all from me.
Hello, my name is Nathan Arkin. I wrote the GUI that enables terrain selection and creates the colors on the map and enables the cursor when the cursor's moved over it for the for the terrain type to be seen. I also implemented what restricts the movement of the GUI. It restricts the movement of organisms. So organisms can't move through different organisms can't move through terrain based on their movement type. Technology I used was Python 3 and tkinter and matplotlib. The original idea was that there would be elevation, that each square on the map would have an elevation associated with it, and based on how the organism was, if an organism was moving to a higher or lower elevation, so it increased the energy expenditure over that space, and as well as make the organism move a smaller distance. Also based on the magnitude of the elevation difference. However, you couldn't really, since it was a bird's eye view, you couldn't really see distinctions in the elevation over the map. So instead, it was decided to have different terrain types, such as rocky, sand, water, or just earth. Also, this gave the chance to have the map be colored, so it made the map look more interesting than just a gray background. My original idea was that the distance an organism could travel over a certain terrain would be reduced, essentially being like a penalty, and it would have a greater expenditure based on its movement type over a certain terrain, but it was easier to have certain terrain just rendered off limits entirely, also preventing an organism from being able to spawn in those areas. Originally, I tried to have a depth first search algorithm that was limited by a maximal distance parameter that would look over, I would look to see if there was an available path that didn't violate the terrain restriction. Though this was very difficult to do when adding the distance restriction. It led to some unforeseen outcomes, and it seemed the breadth first search worked better. However, this greatly slowed the simulation immensely, since every single organism was running the search algorithm. Furthermore, we were only moving one square per frame anyways, so it seemed that it would be better to simply just have the terrain around, just to examine the terrain immediately around it and prevent and restrict any of those squares from being squares that it could travel to. Challenges faced using GitHub. Nathan was not used to using, and I used GitHub for more than 2 years. I was not able to effectively update the local branch with the main branch, and was not effectively dealing with merge conflicts. But some tutorials helped, and some help from teammates helped improve that. Installing certain dependencies were like NumPy was hard, since apparently you needed to create a virtual environment. Which I was unfamiliar with, and so I had to find an article online that allowed for that. Trying to originally program the depth first search algorithm and the breadth first search algorithm was hard. And eventually it was abandoned altogether. Lessons learned were how to use GitHub to keep the local branches updated, and how to resolve merge conflicts, and how to push, add, commit, and push changes onto GitHub. Learned about virtual environments and how to set them up. Ended up gaining greater familiarity with the depth first search and breadth first search, even though they were not ultimately used. Also, learned how to do more GUI programming in tkinter, particularly as it related to creating shapes and geometry. Also, learned some specific stuff about the tag bind function.
This is Sam Baird. The main parts of the program that I worked on is towards the beginning is developing some of the initial backend, so adding day and night and sleep-wake cycles. I also worked on having a text-based representation of the world for early development. So on the right is a screenshot of what the graphical representation was like at the beginning. I also worked on implementing who eats who logic when two organisms collide in the world. Towards the end of the term, I worked more and more on the GUI side. So I worked on implementing saving and loading simulations, tracking organisms and viewing details when you hover over them. I also worked on adding simulation controls, so zooming in and out, panning around the simulation, speeding up, slowing down the simulation, and having pause and resume buttons. I also worked on representing the organism's shape and size. So for technologies used, one package used was the pickle package, and this was used for saving and loading simulations. So it saved the world object as a .world file that you could then load later in another simulation. And we used tkinter for implementing the GUI in Python. Not sure if Python is the best language for graphics programming, but it definitely did the job. The general steps I used for development, or I guess our team used in general, is kind of starting with the initial logic and having a text-based representation to start. And then as more and more features got added into the back end, adding a corresponding visual representation in the front end. For example, using the shape of the organism to represent the organism's energy source. So some challenges in learning. I think originally I had planned to work more on the back end part of the program, but as the term went on, I ended up more or less specializing in the front end. Some challenges I ran into. I ran into many GUI issues with displaying the simulation, especially once you start doing interesting things like zooming in and out. I was able to troubleshoot a lot of this with the help from Jacob and Nathan to organize the graphics into separate layers for the terrain, organisms, and the world. I also had some issues, like logical issues in the GUI code, and so taking a step back and refactoring into separate classes and functions and limiting the shared state helped solve a lot of those issues. And then for overall learning, with this project, I explored a part of Python I wasn't familiar with, which is sort of graphics and UI development. I also became a lot more comfortable with using object-oriented programming and working with the different branches people were working on. I was able to learn Git and GitHub more effectively.
So for my part of the project, the biggest thing that I worked on was the development of an artificial genome. And I have a background in biochemistry, so this is something that I was really interested in seeing how we could get it to work and what it would end up looking like. And so a few of the questions that I started with when developing it were how much inspiration do you take from nature? So you have the central dogma of molecular biology where you go from DNA to RNA to proteins. That's kind of how genetic information is passed along. And that's really complex and would take a lot of effort to put into. And so what you have in nature is something with like a codon table where you go from the DNA ultimately to the proteins. And then how would our artificial genome work? So again, with DNA, you have 4 base pairs, so base 4 system. And I thought it might be kind of interesting if we could use base 2, so with binary, just to kind of make it more computer related. And then that would kind of feed into how complex of a system do we have. So it should be something that's fun and you can kind of follow along with it, but at the same time not so complex that it takes up all the development time. And so the start was with a binary system, and then that became really complex and required a lot of translations and work involved. And so what I ultimately ended up on was each organism has a genome class consisting of a genotype and a phenotype. And so the genotype ended up being a number that ranged from 0 to 50, and then that would be used as the underlying logic in determining the phenotype. And then the phenotype was what I used to determine each trait, and then it's just kind of a more readable version of the genotype. And then each phenotype that an animal has consisted of several different traits, so the reproduction method, energy source, skin type, movement, sleep cycle, and size. And that kind of gave us a very basic organism that we could use. And so looking at just kind of how it works, the energy source, for example, you would have a genotype number ranging from 0 to 50, and wherever it fell along that scale, that's what the trait or the phenotype would be for that organism. And so with this, you could kind of do some basic arithmetic. If you wanted to breed, that ultimately ended up being taking the average of 2 organisms' genotype and then seeing where that fell in, and then any kind of mutation, you could just add a number, subtract a number, divide anything. It would be really easy to work with, but at the same time give some complexity and be modular enough that if we wanted to add more traits or more different phenotypes, that would be really easy to do. And so just kind of looking at how it plays out. So this was an example run of a simulation over 1,000 frames, and you can kind of see how certain traits end up correlating with each other based on the code that we implemented, and then how the other traits kind of, or organisms, interact with each other. And like you see in the top left corner, over time photosynthesis peaks and then falls, and then once it reaches a certain point, sexual organisms are able to get enough energy from them that they're able to start reproducing. And then you just kind of see different ways. So skin was a phenotype that kind of had a smaller impact than other things, so it looks a little more random. And then movement was something that played a big key, and that one kind of correlates with what you see. And so you can kind of see just the different ways that all of these things tie in together.
A possible continuation of the project could be improving the GUI by adding more options that a user could use to undo previously selected terrain features, and also visually it could be changed such that the traits of an organism could be spotted simply on a visual inspection, such that that way it creates a more an apparent picture of the state of the ecosystem and different organisms in the ecosystem, as opposed to having to swipe the cursor over them to view the details and look at the graphs. Other elements like seasonal and weather patterns could also be added to make it more realistic. Given that the simulation mostly emulates life at a macroscopic level, a possible application might be useful is in ecology to simulate an ecosystem. So it could be potentially hypothesize how an ecosystem might change, at least in the short term, as the environment changes. This could potentially be useful to conservationists and policymakers trying to determine what the outcomes might be of different decisions they take. Also, it could be used to predict possible effects of climate change, or at least try out different scenarios for climate change in an ecosystem. That is all.